Okay, in the previous video we have discussed about the aberrations and diffraction of diffraction and the visual acuity. Now we are talking about aberration and the visual acuity. Okay, so yes, definitely in case of diffraction, larger the pupil, better the visual acuity. Larger the pupil, smaller the mar, isn't it? That's definitely case because we know the equation 1.22 lambda divided by n into d. So there is lambda and n which plays major role, and in case of d, larger the d, smaller the mar, and smaller the mar, better the visual acuity. We know that. But if we consider aberration, let's take definitely what we know aberration is our refraction, which is basically minus power or plus power in a sphere or cylinder. There's also second order uh, aberration, and obviously second order aberration decreases our vision, which is very obvious. And even though we correct the second order aberration, there is a lot of high order aberration in our eyes. Even we are emmetropic. So high order aberration also affects the vision, and that's why in previous video I have talked about that's not the case, that's not the only equation, and diffraction is not the only equation. So today we are going to talk about the higher aberration and how it changes and what it affects. So before going there, we must know what is point spread function. So point spread function is image spot corresponding to a single object point, and at the points is the point spread function. So see, in our diffraction system we called it airy disk, isn't it? We never consider it in terms of aberration, but if we consider that airy disk in terms of aberration too, it's far better to explain that airy disk in a point spread function. Point spread function simply means a point from the optical system, and in an image plane or image system, how it spreads. Okay, and definitely we know it spreads if aberration is zero, then it spread like LEDs, isn't it? Especially brighter, darker, and all these things. But with the aberration, it calls point spread function, and sometimes we use line spread functions when we talk, when we object is line, then image also line spread function. When object is point, then image point spread function, isn't it? So we have discussed about this two objects and the minimum angle separation if one peak falls under the, at least falls under the first minima of another uh, area disk, then resolution happens, and that criteria is Rayleigh criteria. Okay, let's move forward. This is the beauty of the book of by Professor Dr. George Smails. See, I have always discussed about it. When pupil size is small, definitely diffraction is in peak, but when pupil size is small, aberration is reduced. At the same time, when pupil size getting larger and larger and larger, diffraction getting smaller and smaller. At the same time, aberration getting larger and larger. So diffraction and aberration with one variable, that is pupil, is a exactly opposite thing, isn't it? So resolution is possible if two targets are angularly separated by at least half of the width of full maxima of their point spread function. So point is basically Rayleigh criteria is same in point spread function. It's all almost the same. That's resolution is happen when the two maxima at least separated by half width of the maximum. Okay, that's simple thing, but we must know what is the difference when we think about it as a point of view. See, in case of we only consider diffraction, point forms perfect airy disk, but if we consider aberration, then it spreads. So that's width spreads, and which means the distance, half of the distance must be larger, isn't it? That's why mar increases, that's why visual acuity decreases. So in this picture, measure point spread function at, see, smaller uh, people. In smaller people, definitely diffraction is one of the point, but not the aberration. When pupil size increases, the point spread functions become broader and broader. So for the resolution, half, at least we need half of the distance, another edge. So the gap between two increases, which means MAR increases, which means visual acuity decreases, isn't it? So that's how we have to understand things. Okay. So same thing. See in this picture. So as the pupil diameter increases, what happens? Minimum angle of resolution increases. Why? Because the effect of aberration. As the pupil size increases, aberration definitely increases, which means pupil size increases, aberration increases, which means MAR increases, which means visual acuity decreases, isn't it? So this picture is very good picture. See, the effect of aberration in this axis and effect of diffraction in this. As the pupil increase, effect of diffraction helps to get minimum angle of resolution. As the pupil size increases, minimum angle of resolution increases, which means visual acuity decreases. So this is a sweet spot, isn't it? So net effect is this. So it's always better. Wait. It's always better to have net effect, something like that. So it's that's why you will see in your book. It's always better to 2.5 to 4 mm pupil is better because they balance both. Okay, this is the case. Just pause the video and see this graph and understand by yourself. Okay, so finally, it's not about diffraction is not our only player. There is aberration too. So they both play in a very contradict fashion. If people size increase, diffraction decrease. If people size increase, aberration increase. So we have to come to the sweet spot, okay, which approximately lies to 2.5 to 4 mm pupil size in diameter. I think I'm clear now. So this is it. So in next video I'll come with another topic. So for reference, I only use this book by Professor Dr. George S. Millis and I think Bistan. Cheers.